Okay, the homework, each chapter is worth 10 points. And that's 3 chapters. That's 30 points worth of homework. The exam itself is worth 100 points. So there are a lot of points in homework. So make sure you turn in the homework. All I do when I grade these is I check, did you do the problem or attempt the problem or not? If you attempted all the problems, then you'll get full credit. But I said something earlier that now I need to clarify a little bit. When I said you can go ahead and copy the answer from the solutions guide, I meant copy the worked out answer, not the final answer, if it's a calculation. If it's a calculation, I'd like to see the setup. And so if all I see is the final answer, then I might not give it any credit for that particular problem. Depends on what it is. If it's like an ABC type thing, then I'd give credit for that. But some of these long calculations, I'd like to see the setup for. A really short calculation, maybe you do it in your calculator. It's all right. Okay, are there any questions on the homework? So chapter 4 I'll collect with the next test. What I'm going to do is, chapter 4 is a lot of review of stoichiometry. There are some more advanced topics in there. We'll come back to those. But before I start talking about the stoichiometry and chemical reactions, I just want to talk about chemical reactions themselves. And so that's mainly the topic of chapter 5. So let's take a look at chapter 5. But the organization of chapter 5, I'm going to rearrange it. I mean, it's not terrible. They start off with precipitation, go to acid base, and then redox reactions. Chemical reactions are what I call chemical properties. And so you probably learn, like in different books, how many different types of chemical reactions are there? You know how many different types of chemical reactions there are in nature? Probably a lot. I mean, probably it's a hard number to count because there's so many different kinds of chemical reactions happening. And so rather than looking at these chemical reactions one by one, we're going to try to group them into different types of reactions. When we group them into different types, there's no strong agreement as to, what are the types of chemical reactions that you should learn. In Chem 4, you're supposed to memorize, I think, 7 different types of chemical reactions. I don't usually have my students do it, but combination, you've heard of those? Combination reactions, decomposition, what else? Combustion, 3. Single replacement, double replacement, precipitation, neutralization. And then Chem 4 does some more. They do like water plus metal oxide, water plus non-metal oxide, etc., etc. But I still find those not very useful, those categories. So let's take a look here. I'll just Google it. You Google it, types of chemical reactions. How many are there? This source says there are 5 basic types of reactions. And so let me click on this link and see what the 5 basic types of reactions are. The 5 basic types of chemical reactions are combination, decomposition, single replacement, double replacement, and combustion. This one says 6 types of chemical reactions. combination, decomposition, displacement, double displacement, precipitation. Well, that's only 5. That's number 6. What are the 6 types? Let's click this link and see if we can see. Oh, here it is. Combination, decomposition, combustion, neutralization, displacement. Well, that's not 6. How many is that? 5.
Maybe if you scroll down. Never mind.
Okay. Maybe, oh, here it is. Combination, decomposition, precipitation, neutralization, combustion, displacement. We got 6. Here's 7. See, let's see what 7 they have here. Combustion, decomposition, neutralization, redox, precipitation or double displacement, synthesis reaction. Synthesis reaction. Synthesis is kind of weird because see, when we do chemical reactions, most of them are synthesis reactions. You're making something from the product. Well, actually, I don't like any of these, personally. So, I have a different organizational arrangement of this. And actually, in my arrangement, there are only 3 types of reactions. And let me tell you what the 3 types of chemical reactions are. The first type of reaction is what I call a metathesis reaction. Another name for metathesis is double replacement. Have you guys done the double replacement AB plus CD? And so why don't I just call it double replacement, instead? Well, the reason I don't call it double replacement is because sometimes they don't follow the AB plus CD pattern. Although they might not follow the AB plus CD pattern, they're still a double replacement style reaction. So for example, you might have a compound AB reacting with CD, reacting with EF. So what do you do if you have an AB plus CD plus EF? Some people will be at a loss. What do you do? I haven't seen that pattern before. But actually you have seen that pattern before because it's just simply a double replacement style pattern. Or you do this. For example, silver ions. Silver ions, do you know what ions silver ions like? Chloride. Silver ions like chloride ions. And what does it form? Silver chloride. Silver chloride is a precipitate. These two are aqueous ions. Normally, if I don't write anything there, it's aqueous. If it's not aqueous, then I'll write solid, liquid, or gas. In this case, solid here. Does this look like an AB plus CD pattern to you? No, it might not look at. To me, it does. Look at, because I need some kind of silver-containing salt, maybe silver nitrate, and some chloride-containing salt, maybe sodium chloride. So this could be silver nitrate plus sodium chloride, which would be an AB plus CD. But we don't know what it is. But to me, this is it. So rather than calling it double replacement, I call it metathesis. And metathesis, like in double replacement reactions, we just swap partners and see, are we getting more favorable ion combinations? And so what I call metathesis is I call these favorable ion combinations. Favorable. How do you know when you have a favorable ion combination? Well, in double replacement, what do we look for in double replacement reactions? We look for precipitation. Like here, this is favorable. Rather than being alone, they like to be together. And this is what we call a precipitate. And so favorable ion combinations have what we call, or what I call, a driving force. Now, I just recently read an article that hates the term driving force. I personally like it. I use it all the time. But I understand their argument. It goes deeper than this. And so there's got to be something driving this. And what's driving this is, forming these strong ionic bonds here. And so precipitation is a driving force. This is for metathesis. So whenever we form precipitate, that's more stable. And if it's more stable, then it's going to drive the reaction. Anything else? Well, how do you know what precipitates? Do you know how you can figure out what precipitates? Solubility rules. Right. And so that's why we want to be familiar with our solubility rules. So we got driving force is precipitation. Consult the solubility rules. What else do we look for?
Gas formation.
Gas formation. So, again, for precipitation, we look at solubility rules, but what do we look for gas formation? How do we know what's going to form gas? Well, typically what people do is they just memorize these. And so what ion combinations lead to gas formation? There's some big ones. So if we have H plus ions, hydrogen ions, they like carbonate. And so when H plus and carbonate combine, do you know what it forms? Oh, I need two H pluses because carbonate's a -2. And so what does it form? It forms H2CO3. Do you know the name for H2CO3? Carbonic acid. And what do you know about carbonic acid? You may have memorized.
It's unstable.
It's unstable and decomposes into
H2O and CO2.
Yeah, H2O liquid and CO2 gas. And so here's our gas formation. We're forming CO2 gas. So when we have an ion combination of H plus and carbonate, we're going to form CO2 gas. All right. Do you know any others? Well, the others that people learn are if we have H plus and sulfite, we're going to form H2SO3. Which is a lot like H2CO3 in the sense that H2SO3 decomposes into similar products. What does this decompose into?
H2O and SO2.
Yeah, H2O plus SO2, sulfur dioxide. Sulfur dioxide is a gas. It'll level out. Another favorable ion combination is between ammonium ions and hydroxide ions. This forms ammonium hydroxide, but ammonium hydroxide is not very stable either. Do you know what ammonium hydroxide decomposes into? Yeah. This is going to decompose into ammonia and H2O. The tricky thing about ammonia is it's quite soluble. Ammonia is what we call a molecular compound. And the solubility rules for molecular compounds is like dissolves like. And so ammonia in a lot of ways is water-like. And so it can either be aqueous or gas, depending on temperature and how much you generate. So those are three common gas formers. There are others. So there's an old rule in chemistry. Don't mix acid with sulfide salts. Because let's say you have acid here and you have sulfide. Do you know what it makes? Hydrogen sulfide. Hydrogen sulfide is easy to detect with your nose because it gives off a characteristic odor. Rotten egg. This is a rotten egg odor. Most sulfur-containing compounds have foul odors associated with them. In fact, there was a problem in your book. I didn't assign it. I was thinking of assigning it or giving it as an exam question. I didn't do that. But I was tempted to do that for this last exam. I was thinking, yeah, this might be interesting, but it's number 95 here. 95, in the year 2000, the Guinness Book of World Records called ethyl mercaptan C2H6S the smelliest substance known. Mercaptans, you know what mercaptans are? Mercaptans are an organic functional group, and they're analogous to alcohols, except the difference is rather than having oxygen, they have sulfur. And so that's not really the best way to write it. You know, the best way to write it is something like this: CH3, CH2, and ethanol would have an OH, but rather than an ol, we call it a thiol. You know, thio means what?
Lose an oxygen out of sulfur.
Yeah, lose an oxygen out of sulfur. And so this is called ethane thiol or ethyl mercaptan. This is mercaptan, is the, lose the oxygen, replace it with a sulfur. That would be it. This would be ethyl mercaptan or ethane thiol. And this holds the world record for the smelliest substance known. When I was at UCSB, I worked with lots of these mercaptans. They were, it was tough, basically, because of the smell. It was so bad. But you know, I used to work with this stuff all the time. Ethane thiol, I called it. It wasn't that bad. There were worse. So the Guinness Book of World Records, maybe they just smell differently, but I'm not sure. But probably the worst smelling one I used was, rather than sulfur here, it had a selenium, Se. And that smelled really bad. Yeah. So I'm working in the lab with all these things. It's not very pleasant. And then my clothes would smell like it. You know, my skin would smell like it. Hair, everything smelled like this. So what did you do? What I used to I used to be in much better shape, because after lab I would go to the gym, and then what I'd do is I'd get on the treadmill and then I would run for 6 miles on the treadmill in an effort to sweat out all the mercaptans that I absorbed in the skin, and then in my lungs, you know, I had lots of mercaptan. I wanted to exhale it all out. And so after 6 miles, I felt pretty good. You know, like I sweated it all out, but it's nasty. When I was at UCLA, one of the people in our research group, he told me that he bought a brand new pair of expensive tennis shoes. This is so many years ago. They were $100, which was a lot of money back then. You know, $100. You think about this. You know what the quarterly tuition at UCLA was at that time? $450. So he had a $100 pair of sneakers, and tuition at UCLA was $400. Well, it's not really a fair comparison, because tuition is just skyrocketed. You know, like inflation's gone up like this, but tuition, I don't know why it's so crazy. How expensive college has gotten. Still, they consider UCLA now as a reasonable value, but tuition at UCLA is a lot higher than what it was. But getting back to the story, he spilled one drop of thiol on his sneakers, and brand new, first time he wore them. He shouldn't have worn them to the lab, but then he tried cleaning them. I don't recall exactly how long he spent, but he spent a lot of time trying to clean it with so many different things. And then I think it was after a month or so, gave up and then just threw them in the garbage. They smelled too bad. So these are pretty bad. So we don't want to mix acids with sulfides because we're going to make, not only do these smell bad, but they're pretty toxic. So H2S. H2S has a bad reputation because what happens is it's really pretty toxic. So you could be exposed to this stuff, hydrogen sulfide gas. Initially you're going to smell it, but after a little bit of time, your sensory receptors in your nose get saturated and you can no longer smell it. And so it smells bad and then the smell goes away. And so a lot of people think when the smell goes away, then the H2S has gone away. But what they didn't realize is their sense of smell has been totally fatigued and they can't smell it anymore. So it's happened that people have died from H2S exposure. There's a case, I think it was about 10 years ago in Ventura, where somebody died from H2S exposure. Since you can detect it at the part per billion level, in fact, this is what this says. The average person can detect its presence in air at levels as low as 9 times 10 to the minus 4 micromoles per cubic meter. They express the limited detectability of alpha mercaptan in parts per billion. So this would have been a dimensional analysis problem. Thrown out. H2S is detectable at the part per billion level. This is also quite toxic. They say never mix acid, H+, with cyanide. If you mix acid with cyanide, what do you form? Hydrogen cyanide, which is a gas, and also very toxic, etc. So we look for these kind of things that form gas. And there's one more thing that we look for. What's the one last thing that we look for driving force?
I can't remember which way it goes, but it's like strong acid, the weak acid, or vice
Well,
versa.
it doesn't have to be a strong acid. It doesn't have to be like one of the 7 strong acids. It just has to be stronger. And so the final thing we look for is going from a stronger acid to a weaker acid. Stronger acids are less stable, more reactive. Weaker acids are more stable, less reactive. And so when we look at all these, we're trying to form stable products from less stable reactants. And that's what the driving force is. It's going from less stable reactants to more stable product. How do we know when we're going to more stable? Well, we look for these things: precipitation, gas formation, stronger to weaker acid. Now, stronger to weaker acid, you have the 7 strong acids, right? But what about all the other acids out there? So, for example, oxalic acid versus acetic acid. Do you know which one's stronger? Which one's weaker? No, not necessarily. You might know if you've seen this chart enough times, but it's not something you have to memorize, fortunately. You know, the solubility rules I want you to memorize, and other things I want you to memorize, but fortunately, this you don't have to memorize. So what's the strongest acid on this chart? Perchloric, and then, here, this this is 6 of the 7 common strong acids. Hydronium's written here because hydronium is the strongest acid that can exist in water. So if you have any one of these acids, what happens is it completely dissociates, or it reacts with water molecules to form hydronium. Whereas if you go below hydronium here, then we have these weak acids. And weak acids don't dissociate 100%, they partially dissociate. And so we have some weak acid present, as well as some of the dissociated things. And so if I'm looking at oxalic, unfortunately oxalic's not on this chart here, but it's up here. And then we look for acetic acid. Acetic acid's here. And so we could see which one is stronger. The ones that are higher up on this chart are stronger. Ones that are lower. So we look at our reactants and products and see, are we going from stronger to weaker? If that's the case, then this is kind of the downhill reaction. You know, it's favored in the downhill direction. All right, so that's metathesis. The second type of reaction, here. For stronger to weaker acid, we just consult the acid chart. The second type of reaction, there's a little bit of overlap here, but we'll call it acid-base reaction. We'll talk more about acid-base reactions in this chapter and future chapters. In acid-base reactions, we have 2 types of acid-base reactions. The first type is the Bronsted, or Bronsted-Lowry. Bronsted acid is a proton donor. So most people know Bronsted acid, proton donor, donates a hydrogen. This is why it's important. You see the proton donors here in red. Red. Except when we get to acetic acid, do you see where the proton is donated? At the end. The only time it's written at the end is if it's a carboxylic acid group like this. Or sometimes they'll do an alcohol like this, but alcohols, are they very good acids? No. And so these are getting into exceptionally weak acids. Here. Ammonium, sorry, there's another case. So bronze says proton donor, proton acceptor. And then we have Lewis. I think I wrote this the other day, but Lewis is defined a little bit differently. The acid in the Lewis definition is defined as the what?
The electron pair acceptor.
The electron pair acceptor. Both of these accomplish the same thing. So all Bronsted acids are also Lewis acids. So all Bronsted acids are Lewis acids. We can look at it either way. When we have a Bronsted acid-base reaction, it looks just like a Lewis acid-base reaction. But we can't say this. We can't reverse that and say all Lewis acids are Bronsted acids. That's false. And so what we have is we have these 2 definitions. Why do we have 2 working definitions for an acid? One, sometimes it's just easier to analyze Bronsted acid base. This you see this acid chart here? This acid chart here is only for Bronsted acids. Do you see a Lewis acid chart? You don't see a Lewis acid chart because they're a lot more complicated. And therefore, since Lewis is a lot more complicated, we'll try to simplify our life by just looking at a small part of the acid-base universe. If we just look at the small part of the acid-base universe, then we'll just zero in on Bronsted. try to understand those well. Later on, we'll tackle the Lewis in more detail. The driving force for acid-base reactions, I like to do this. I like to go SA, SB to WA, WB. Do you know what these represent or stand for?
Strong acids.
Yeah, not strong, but stronger. It could still be weak. So as an example, let's say our stronger acid were nitrous acid on the left. And then we look on the right side, the product side, and the strongest acid is water. So if we go from nitrous acid, which is a weak acid, to water, it's still going from stronger to weaker, because water is much weaker. And so it's a stronger acid. SB, yeah, would be a stronger base going to weaker. Acid and weaker base. Okay, and then the third type of reaction is redox. Redox is, when we look at Lewis is what we call electron pair donor. But in redox, the electrons are taken by the oxidizer. And so it's electron transfer, let's say. They're taken from one atom to the other. But in the case for Lewis, it's not like that. They end up sharing the electrons. So electron transfer reactions. In these electron transfer reactions, what we look for is the driving force. Let's see the driving force here. DF. In redox, we have a similar looking driving force. Which is going to be SOA, SRA to WOA plus WRA. Do you know what those stand for? SOA.
Stronger oxidizing agent.
Yeah. Yeah. So we need to go from a stronger oxidizing agent and a stronger reducing agent to weaker oxidizing agent and a weaker reducing agent. So how do we know what's stronger and what's weaker? Some of these you can kind of figure out. Some of them. But typically, oxidizing agents are electron poor or electron rich. Electron poor. Oxidizing agents are electron poor. If you think of oxygen, O2, it's electron poor. Why? Well, O2, when we look at the oxidation state, it's 0. So it has 6 valence electrons. It's supposed to have 6 valence electrons. The oxidation state is 0. Is that really electron poor? It's electron poor because of what it could be. What does oxygen want to be in terms of oxidation state? -2. It really wants to be -2. And so in that context, then yes, oxygen is electron poor. And therefore, electron poor species are good oxidizers. So oxygen is a good oxidizer. Where can it take the electrons from? It can take them from metals. So oxygen loves to oxidize metals, take the electrons off metals. Do that. And so some of these we can kind of figure out. Others we just look it up. There's a chart, call it the redox chart, that we can use. Like the acid base, we don't have to memorize all the acids. We don't have to memorize all the oxidizers. We consult the redox chart. To do that, to figure it out. Okay, why don't you give it some thought here? Let me pause it. Why don't you tell me this? I have a question for you. What are the chemical properties of what are the chemical properties of hydrochloric acid, HClAQ? Now, speaking of UCLA, when I was a student at UCLA, I had to take an oral exam. Oral exams are pretty rare there. You know, another thing that skyrocketed is the class size. Let me go back to inflation. The class sizes have inflated at UCLA. I was there a couple of years ago, and I spoke to my old advisor there, and he told me, you know, his class has 150 students. When I took that class, there were like 20 students in the class. You know, so it's gone from 20 students to 150 students, and tuition has also skyrocketed. So I don't understand that quite well. You'd think they'd have a lot more professors that are teaching it, but anyway. I had this oral exam, and one of the questions in the oral exam is, what are the chemical properties of phosphate? And so, you know, like many students, I went through, I knew about precipitation reactions, I knew about combination reactions, decomposition reactions, double replacement. I was good at double replacement. AB plus CD, I could do those all day. Single replacement, no problem. But when I got thrown a question like that, what are the chemical properties of phosphate? I couldn't really. I mean, I started thinking in the back of my mind, you know, where have I seen phosphate? You know, where I saw it was just reading the ingredients, like laundry detergent. Have you ever read the ingredients of laundry detergent? Trisodium phosphate, you know, Na3PO4. Not used, you know, trisodium phosphate's not the way we name it in chemistry, but that's the way they name it on the detergent box. I remember that. But there's a lot of awkward, you know, silence. I couldn't think of anything. Fortunately, there were other questions. You know, if that were the only question, I would have bombed that test. But after, you know, some time of thinking, I couldn't really come up with much, and they were generous enough to move on to another question, which I could answer. But anyway, so that got me thinking. You know, okay, you have, you know, 5 categories of chemicals, 6 categories, 7. Actually, what was the most? What was the most here? In Chem 4, it's like 9. I think there's 9 types of chemical reactions that I was supposed to have you guys memorize, but I never did because I didn't like the way it was organized. I think the most they gave here were 12. Yeah. 12. Anyway. Yeah. So why don't you give this a little bit of thought? You know, what are the chemical properties of HCl? Let me pause it for a second. Okay, do you have them? Some?
Would one be, I think, a strong acid and a weak base? Would that be
Strong acid and a weak base.
Would that be
Mm-hmm.
a strong reducing agent?
A strong reducing agent?
I get them switched around a lot.
You got
so
it flipped.
I got it flipped, okay.
A moderate, not reducing, a moderate
Oxidized,
and an extremely weak.
reducing.
Yeah, so far you're doing much better than I did on the phosphate question. That's good.
In anatomy, you're just focusing on what's gaining or losing, not what's taking or giving, so I switch
Okay.
them around.
Okay. And then, any others?
Electron, no, because if I got that one wrong, I want to say it's electron rich.
Electron rich?
Yeah.
Yeah, electron rich, electron poor. You have to have some kind of like, guideposts. You have to have some kind of reference, like some kind of frame of reference in order to figure out rich and poor. It's electron poor, but it's a little bit tricky because we look at it differently. Anybody else? Anything to add to that?
I said it was polar.
Electron poor?
No, polar.
Polar? It is polar. Polar, though, is more physical. You know, it would be more like what it dissolves in what, rather than attack things chemically. But polarity is also related to chemistry, too. Just ran out of water. So let's take a look. Well, HCl. You know, there are different levels that we can just try to analyze it based on the formula. You know, when we try to analyze things based on the formula, we look at how the electrons are distributed in there, and so we'll typically do oxidation states, formal charges, octets, this kind of stuff. I'll take a look at that in a little bit. But for right now, when we have HCl, HCl is a strong electrolyte. And so a solution of HCl contains H plus and Cl minus. H plus and Cl minus, do they have the exact same chemical properties? No, so what we do is we look at them separately. You know, yes, they're there together and they're going to impact the overall properties of HCl, but I tend to look at these separately and then determine the properties here. Because you said HCl is a strong acid, weak base. Why did you say a weak base? Because normally when people think of hydrochloric acid, that's one of the 7 common strong acids. And so you're calling it a weak base because?
Usually that from last lesson, when something's usually a strong acid, it tends to be a weaker base.
Okay,
I might use that.
well, it's true, it is a weak base also. But let's break it down. So the problem is, you know, I got to ask that question, but I didn't have a systematic way of answering it, or an organized way of answering it. And so this is why I like this. I don't like how the chemical reactions are organized in the book. And so I try to follow the book, but in this case, I'm going to deviate significantly from the book. You know, however many different types of chemical reactions they give in the book, I don't really care because I'm not going to organize it that way. I think our book does the same: combination, decomposition, etc. Instead, I'm going to say, okay, if I want the chemical properties of HCl, then I should look at these 3 types of chemical properties. There are 3 types of chemical properties. So if I want a comprehensive list of chemical properties, or, you know, it's not, well, there are some some reactions that fall outside the scope, but those are like photochemical, this kind of stuff, that kind of stuff. So there are three basic types of chemical reactions. What are the three basic types of chemical reactions? Metathesis. Metathesis, another way of thinking of metathesis are,
Double replacement.
or, another,
Favorable ion.
yeah, okay, if you did double replacement, tell me everything. Okay, this is our AB. AB, double replacement's AB plus
3D.
CD. Tell me all the CDs HCl to react with. A lot. Do you want to sit there and list all of them? NaOH? Check, yes. KOH? Check, yes. LiOH? Yes. CaOH2? Yes. A lot. I mean, we could be there for infinite amount of time trying to come up with a comprehensive list of everything. A lot. So instead, what we're going to do is we're going to look at H+, and we're going to look at what ions does H+ like. And so one of the clues for H+ is this is an acid. It's H+ or H3O+. And so what ions does it like? It likes basic ions. And so this acid likes base anions. So what are the anions that H+ likes? And so we go back up to our chart here. And we have a all-in-one. So we already see the acid. The strongest acid on the chart is perchloric. It's a pretty powerful acid. What is the weakest acid on this chart? Yeah, the weakest acid, this isn't even considered an acid. Do you consider methane an acid? Not at all, but if you have a super base, then the super base might be able to pluck a proton off, a hydrogen ion off methane. If it plucks a hydrogen ion off methane, what does it form? It forms CH3 minus. CH3 minus, do you know what we call that? Methide. Methide is very unhappy. Methide is an extremely powerful base. So methide really wants to take a hydrogen off anything it can come into contact with. And so this is what we call a conjugate base, and this is a conjugate pair. So methane and methide are a pair. That is, when methane loses a proton, it forms methide. When methide gains a proton, it forms methane. There's going to be a seesaw relationship. So if one is weak, like down here, the opposite is going to be strong, way up here. So methide's got to be strong because it really wants hydrogens and it really doesn't want to let go of them. So once it gains that hydrogen, it forms CH4. CH4 is extremely hard to take off that proton. Whereas we can see the conjugate relationship here. If HClO4 is a strong acid, its conjugate must be extremely weak. And that is, HClO4 easily loses the proton, the hydrogen ion. That means perchlorate must not hold on to it very well. Perchlorate is its conjugate. And so strong acid, perchloric acid, makes a weak conjugate base, perchlorate. And so these are our bases here. Not all these bases are ions. Remember, metathesis is favorable ion combinations. So this is why I say base anions, not just base. Because, for example, water is not an ion. Well, everything else is an ion. So there. Going down. Ammonia is not an ion. And so everything else is an anion. And so what will H plus react with? Well, will it react with perchlorate? plus react with the perchlorate, the weakest base on the chart? Yes or no? Now we're going through the list, but we're going to make the list a little bit easier. Will H plus react with perchlorate? Actually, to answer that question, let's take a look at this. H plus and hydronium are the same thing, basically. I mean, H plus is a shorthand or abbreviated way of writing hydronium, and we need a water in there. H plus itself is pretty unstable. So let's look at an acid here. And so if I have this H plus, it can attach to a water molecule to form hydronium, like this. Now, this hydronium ion can react with a base. The base we're going to react it with is just water. So there are two ways of looking at this. One is Bronsted, the other is Lewis. In this case, I can look at it either way, either Bronsted or Lewis. I'm going to look at it in terms of Lewis. I'm going to look at it with this electron pair pushing into that hydrogen, like that. And so this water is going to try to pluck that hydrogen ion off, the H plus off. Will it be successful? And so what's going to result is a tug of war. And the tug of war is going to look like this. This is trying to pull off that hydrogen, so this is starting to break free here and be pulled towards here. So we end up in a tug of war for the H plus. The proton. Who wins? Will the left water win, or will the right water win? Who wins? Yeah, neither. I mean, it's kind of random, because you know why it's random? This is a tie. So maybe sometimes the right water will win, sometimes the left water will win, but we'd expect it to be kind of 50-50.
Is that because of the movement of the, like, electron clouds, basically? Is that what it is?
Yeah, it's, well, both of this oxygen has some kind of electronegativity. It's trying to pull. Actually, not. Well, let's just say there's some. Maybe not electronegativity is not the best way of phrasing this. Probably the best way of phrasing this is there's some charges associated with these atoms, and so these oxygens have what we call a delta minus or partial negative charge, and both of them are going to be attracted to this. Here. And both of them are going to try to take it. But what's going to result in this case is a tie. Okay, what if we replace this water on the right with perchlorate? Do you think perchlorate's going to be stronger in this tug of war for the hydrogen? Is perchlorate a stronger or weaker base than water? And so we look at the base chart's flipped upside down, so you can see the base strength is at the bottom. So the strongest base is at the bottom, the weakest base is at the top. If we threw methide in there, so if there's a tug of war between water and methide, who's going to win? Methide. Methide has no problem plucking hydrogens off anything. It'll just go up and pluck it off. Methide's strong. But what if we have perchlorate? Perchlorate versus water? Perchlorate's the worst base on this chart, but is it strong enough? You think? No, it's not. No, it's not. And so if it's weaker than water, nothing's going to happen. So any base weaker than water, nitrate, chloride, bromide, iodide, bisulfate, perchlorate, nothing's going to happen. We need a base that's not weaker than water. We need a base that is stronger than water. So if I replace this water with something stronger, well, what's stronger? Sulfate's stronger. So if I replace this water with sulfate, then sulfate can pluck it off because it's stronger. Does that make sense?
You were saying, in terms of HCl, to look at them separately.
Yeah.
And figure out the properties. So is it a weak base because the chloride?
Yes.
Is a very weak?
Right, exactly. That's important. Yeah, we look at it separately because if you look at this, yeah, we have a pretty strong acid here. But in HCl, we also have a base, chloride, and that's here. But when you look at the base, is it very strong? No, it's extremely weak. It's weaker than water. And so chloride being even weaker than water, it's not as significant as the acid. And so normally when people look at HCl, they don't say that's an acid and a base. They just say that's an acid. And that's a strong acid because the chloride is so terribly weak it can't really do much of anything. Okay, now we can generate a list easily. Water will, H plus or hydronium will react with all bases stronger than water. And so if you wanted to generate a list, that would be sulfate, dihydrogen phosphate, fluoride, nitrite, acetate, bicarbonate, hydrogen sulfide ions, cyanide, carbonate, hydroxide, etc. And so if we have a different base chart, if you look at that base chart, it's a bit more comprehensive. And so anything stronger than water would start off with hydrogen oxalate ion over there. Go to bisulfite, sulfate, dihydrogen phosphate, etc. And go along. Chloride, on the other hand, is a base. Well, actually, no. There's a little bit of overlap here because I'm not talking about acid-base reactions right now. I'm talking about metathesis. But for H plus, we need to do it because H plus is acid. And it's going to react with bases, base anions. So the favorable ion combinations would be anything reacting with a base, like cyanide. So H plus cyanide yields HCN. Now HCN is a weaker acid than H plus, H3O plus. And so we're going from stronger acid, H plus, to weaker acid, HCN. So that would be the driving force for this. Chloride likes what? Well, let me tell you, chloride likes silver ions. You know, when silver ions and chloride come together, do you know what forms? AgCl. Is silver chloride soluble or insoluble in water? Insoluble. And so this forms a precipitate. We get precipitation. But again, it's still just a metathesis reaction. What else precipitates with chloride? Lead 2. We have PbCl2. And one more. Mercury.
Is mercury 1?
Mercury 1, which mercury 1 is Hg2, 2 plus. So we're going to form Hg2Cl2. So these are the favorable ion combinations here. So anyway, H plus likes base anions stronger than water. Okay, so the first thing is metathesis. What are the metathesis properties of HCl? Well, these are the metathesis properties of HCl. Can I do any gas formation with chloride? No. We could go to, chloride's not an acid, but we could go from stronger base to weaker base. That's a possibility. All right, 2, we're going to look at acid base next. To keep our life simple, we're going to look at Bronsted acid base primarily. Look at this. Okay, metathesis is favorable ion combinations. Acid base, it doesn't matter if it's an ion or not an ion. And so for acid base, H plus likes all bases stronger than what? And so H plus reacts with all bases stronger than water. Chloride is an acid. Chloride's a base. And so we kind of do the similar thing here with chloride. Let me show you what I'm talking about. Do you see chloride? There. So we kind of frame it in the same way. Here's a chloride. If chloride got in a tug of war with HCl, who would win? So this chloride's going to try to take the hydrogen here, and we're going to end up with a tug of war like this. Which chloride would win?
Tie.
It's a tie. And so what we need is we need a stronger acid than HCl. Are there any stronger acids than HCl? Yeah. What are the stronger acids than HCl? Yeah, a stronger acid means it loses the hydrogen easier. So what loses the hydrogen easier than HCl? Yeah. Hydrogen bromide or hydrogen bromic acid. And so HBr is a stronger acid, which means it loses the hydrogen easier, which means if they got into a tug of war, chloride versus bromide, who would win? Yeah. And so if we had a tug of war between bromide and chloride, you know who wins? Chloride's going to win. There are different ways we can think of it. You know, if you've been looking at this pattern for a long time, why do you think chloride would win the H plus? Yeah, it's a stronger base, but why is it a stronger base? Why is chloride a stronger base than bromide? Or not its electronegativity, it's because of its charge is more dense. It's because of its size. Chloride is smaller than bromide, and so it's going to have more concentrated negative charge. So one way of visualizing this is we got a big bromide here and a small chloride. Even though they're both negative charges, which one is the H plus going to be more attracted to? To the right. It's got a higher charge density. And so what that means is that chloride should react with any acid stronger than hydrochloric acid. And so what we say is reacts with all acids stronger than HCl. Does that make sense for that? Maybe not, but if you know the pattern, you can just repeat the pattern. You keep repeating the pattern, eventually it might click. I need to put a little asterisk here. This asterisk, I'm going to write a little footnote here. Leveling effect can alter our prediction. I'll talk about what the leveling effect is later on, not right now. Okay, in terms of relative strength, as far as acids go, H plus, where would you rank that? Strong, moderate, or weak? Strong. And as far as chloride goes, where would you rank that? Strong, moderate, or weak? Weak. And so which property do you think most dominates in HCl? Is it the acid property of HCl or the base property? The acid. So this is why we call it hydrochloric acid. And really, base property is not so significant. All right, one more to go, and then we have the chemical properties of HCl pretty well covered. What was the third type of reaction? Redox. Oxidizers are electron rich or electron poor?
Electron
Electron
poor.
poor. Reducers or fuels are rich. H plus. Is H plus poor or rich? Seems to be poor. It's got a positive charge, right? Seems to be poor. How poor is it? So here we don't do any memorizing. You aren't going to have to memorize this chart here. This chart will be given, the acid-base chart. Nor will you have to memorize the redox chart. The redox chart will be given as well. So let's take a look at the redox chart. The redox chart, if we gain some familiarity with the redox chart, it will tell us how electron poor H plus is. So let me grab one of these redox charts here. This is a simple one, it looks like. Organization is a little bit different and a little bit the same as the acid chart. On the left side, you know, we have the oxidizers, the reducers. Then we got to ask, what do oxidizers do? Do they take electrons or do they lose electrons? Oxidizers take electrons. And so all these are oxidizers. Look at F2. What's the F2 doing? It's taking 2 electrons. In the process, it's going to form 2 F minuses, 2 fluorides. And so on the left side, we have the oxidizers. The oxidizers are electron poor species, so based on this chart, which species is the most electron poor? Fluorine. This is the most electron poor. But how can that be? Look below it, cerium with a 4+ charge. Wouldn't that be? No. Turns out fluorine still is. But what about permanganate? Permanganate has a negative charge. A negative charge means it has an extra electron. Why is permanganate on this list?
Because manganese is +7.
Yeah. Permanganate is really electron poor. Let's write that over here. Not because of the negative charge, having that extra electron. It's MnO4 minus. It depends on where that negative charge originated from. And I'll tell you where the negative charge originated from. How do these oxygens look? And then I have some terminology for this. The terminology I use is electron poor, electron rich, and just happy as is. And so oxygen with a -2, is that electron rich, electron poor, or happy as is? This is happy as is. And what I do is I have some points of references, a reference frame, like H2O. Is H2O stable? Yeah, H2O is stable.
Because everything has
Stable meaning, is it very reactive? Is water chemically very reactive? No. So H2O is happy. It's a happy molecule, right? It's happy as is. What are the oxidation states? Do we do hydrogen or oxygen first? Hydrogen gets plus,
1
and then oxygen is,
-2.
and so oxygen's happy at -2. In fact, when we look at the periodic table, for oxygen to get that octet, it needs to be like neon. And so oxygen needs to gain 2 more electrons to be like neon. Oxygen has 8 electrons and wants to go to a total of 10. And so these are happy as is. Is there an extra electron here? No, there's no extra electron. If oxygen only had 1 minus rather than 2 minus, then it's like fluorine, but fluorine's not happy. And that leaves manganese at plus 7. So where did this negative charge come from? It came from one of the oxygens. In order to satisfy the octets for all 4 oxygens, this gives us a total of -8 plus 7, which is going to give us -1. So even though it might appear electron rich, no, the oxygens are electron happy. Electron rich species are good fuels. Is water a good fuel? I saw this on a video, YouTube video. If you run out of gasoline, can you put water in your gas tank? Will that burn? Well, you might say oxygen. Oxygen is electron rich. It should burn, right? I should be able to burn water in my engine. Is that going to work? No, not at all, because oxygen is happy as is. Is manganese very happy here? No, manganese is terribly unhappy. Manganese being terribly unhappy, this is why it's ranked number 3. You don't see much cerium. And if you don't see much cerium, it's like number 2 on this chart here. So fluorine is the least happiest, most electron poor, followed by permanganate, followed by chlorine, followed by oxygen. Oxygen is the prototypical oxidizer. That's where the name oxidizer comes from.
What oxidation state would manganese be happy at?
What oxidation state would manganese be happy at? Manganese would be happy at manganese 0 or manganese 2+. These would be considered happy. But manganese has oxidation states all the way from 0 to +7. And so, for example, if we're in, this is reasonably happy too. MnO, that's manganese 2 plus. MnO2, that's manganese 4 plus. Manganese 4 plus, this is a stable compound here. It's not necessarily because manganese 4 is happy, but this is called desert varnish. And so if you ever go out in the desert and you see a black varnish-like coating on the rocks, the sandstone out there, it's MnO2, manganese 4 oxide. And so what we do is we try to reference it, we try to have a frame of reference of chemical compounds and their relative stability. And so let's, if we look at desert varnish provides a very protective coating on there. And it's very tough coating. And so this stuff doesn't wipe off. In fact, they're petroglyphs in this one. They have the chisel in there. If you've ever been to Valley of Fire State Park, they have these beautiful petroglyphs chiseled into the desert varnish out there. It's like a glass or ceramic coating. It's very tough. Rock rust, desert varnish. Basically. And so it's very tough, this coating. And so that makes you think, oh, it's pretty stable. But there are other things in addition to this, you know. I mean, getting +4 is starting to get high. And so a lot of these, you just look at the types of compounds it makes. But if you're looking at ion, like manganese ion, then +2 would be it. +3 is starting to get more reactive. This is the two-pronged approach to chemistry. The two-pronged approach is we know how to do the oxidation states. You just follow the rules. But how do you interpret those oxidation states? How you interpret those oxidation states is we have to have some kind of reference frame. You know, we have to have like some factual knowledge memorized. Like for example here, let me just finish off with this. Bleach. Bleach, what are the oxidation states here? Which one goes first, sodium, chlorine, or oxygen? Sodium at +1, then what? Oxygen at -2, and then? Chlorine's going to be +1. So here we have sodium's +1, chlorine's +1. Is sodium happy at +1? Yeah, I mean, you eat it all the time, sprinkle on French fries. I like the taste of sodium. Tastes good. Is chlorine happy at +1? No, chlorine would be happy at what? -1. So this chlorine is terribly unhappy. And this is going to be very reactive. This is bleach. Bleach is one of the things that my friend tried to get the smell off his tennis shoes. Usually bleach works. Bleach works wonders, but it wasn't able to kill off all the odor in his shoes. And so it depends. This is very electron poor. But then you go to CO2. What are the oxidation states in CO2? Oxygen is, carbon is, so surely +4 has got to be more electron poor than +1, right? +4 should be, so, you know, instead of using bleach, my friend should have tried using CO2, you know, exhaled on his shoes. Do you think that's going to be strong enough to oxidize? No, because we know CO2 is fairly stable. So +4 is okay. You know, it's reasonably happy oxidation state. And so what's happy is you have to memorize it element by element by looking at the reactivity of compounds with different oxidation states for that same element to get an idea. And so for manganese, you do that. Manganese 2 in solution is very stable. Manganese 2 plus in water forms pink solution. And so manganese 2 plus is no problem there. Okay. All right, well anyway, I'm out of time, so we're going to continue chemical properties. next time.